Okay, so this week we're very happy to have Elliott tell us about wormhole renormalization. So Elliott, go ahead.
Um, Hi, so yeah, thank you very much for the invitation. I'm very happy to talk in your seminar. So today I'm going to be telling you about a paper that we put out last year with Matilda Marcoli and Jake McNamara, which is about wormhole renormalization. Okay, so the motivation of this paper is the fact that in the last few years, the gravitational path integral has proven to be a very, very valuable tool to understand quantum gravity. So we've derived many wonderful things with the gravitational path integral, for example, the Page curve of black hole evaporation. And that's given us a lot of reasons to, take it seriously. So it seems to know about many non-perturbative aspects of quantum gravity. On the other hand, if we take the gravitational path integral at face value, it looks like it contradicts some principles of the holographic constraints. For example, one that we will see today is the factorization puzzle. So we're in a bit of a strange situation where on the one hand, we really like the gravitational path integral because it seems to know a lot about UV physics. But on the other hand, it's still not completely consistent with this UV physics. And so that leads to the question of how to ameliorate the gravitational path integral in order to keep its good features, but at the same time, be able to make it consistent with what we know about holography. So this talk is very much ingrained in that philosophy. And for today, I'm going to be asking this question in the particular context of the factorization puzzle, which I'm about to explain. Okay, so what is the factorization puzzle? Well, the idea is that in the gravitational path integral, you have wormholes, and this is somehow a problem. So, let's consider ADS-CFT. And let's say that we're interested in computing a two-boundary partition function. So let's say we're interested in computing the partition function of the CFT on two disconnected boundaries. So, I put my CFT on this sigma 1 here and this sigma 2 here, and they form a disconnected boundary condition. Then, by axioms of conformal field theory, because conformal field theory is a local theory, I know that this partition function is going to factorize as the product of the partition function on sigma 1 and the partition function on sigma 2. Okay, so that's obvious from the conformal field theory side. But now I can try to ask the same question from the bulk. And so, of course, nobody really knows what the path integral we should be doing in the UV complete theory should be. But for many things, the gravitational path integral has been a good guess, a good approximation. So we could try to do that. So we try to compute the same partition function using the gravitational path integral with this same boundary condition here. And so what are the rules of the game in the gravitational path integral? Well, we sum over saddles, and for each saddle, we sum over the fields on the saddle. So the first saddle that will contribute will look like this, two disconnected disks with these boundaries. But then, because we're in gravity, we should also sum over topologies. And so, for example, we would also have a wormhole like this. This is a wormhole that would contribute to the sum. And then you would have higher topologies and so on. So now we're interested in factorization. So if we look at the functional integral on this background, because this background is disconnected, there's no obstruction to factorization there. We would also get something that factorizes between the left and the right. But because this wormhole here is connected, then its contribution to the gravitational path integral will not factorize, and it will be an obstruction to factorization. So this is an obstruction to this factorization property here. And so that's the essence of the factorization puzzle. It is, how do we reconcile this UV complete property of conformal field theory, which is factorization, to the presence with the presence of wormholes in the gravitational path integral. So this has been noticed for a while, and there have been quite a few resolutions that have been floated around for a bit of time. So let me summarize some possible resolutions that have been proposed in the literature. So the first type of resolution, which I think was very popular until 2019, was to just say, well, maybe there's some kind of UV complete principle in string theory that tells us that we should actually not be summing over wormholes. So if instead of computing a full path integral, we exclude by hand the wormhole saddle. So we say that we just have terms that are disconnected between the two sides. Then we get rid of the problem because we've decided that there is some exclusion rule that precludes the existence of these wormholes. So that's kind of the easy way out. And I guess pre-2019 we had some reasons to sum over wormholes, but none of them were too serious. So we could be inclined to take this picture seriously. But the problem is that in 2019 and the next years, we realized that summing over wormholes in the path integral was actually very important. For example, it's the crucial part that allows you to get the page curve in black hole evaporation. So for that reason, it becomes a bit difficult to just say, oh, we should not be summing over wormholes. We would somehow like to sum over these wormholes and still get rid of this factorization puzzle. And then, of course, if we're summing over wormholes, the idea is that we're going to have to add something else to the game. Because at phase values, these wormholes disrupt factorization, so we need something else to cancel their effect. So those two other solutions here are basically two ways of adding something that restores factorization to the wormholes. And in both cases, adding this thing means going beyond the semi-classical physics of the gravitational path integral and doing something that is non-local. So the first possibility that was proposed that I want to talk about today is the possibility that what we could do is we could say, okay, the gravitational path integral sums over wormholes, but we're also going to add some type of non-local contribution to the path integral. So for example, what Maroff and Maxfield proposed in 2020, so this was first proposed in a paper by, oops, sorry. And this was first proposed in a paper by Maroff and Maxfield in 2020, which is to say, okay, I'm going to sum over wormholes, and there's going to be many spacetimes that are going to appear in my path integral, but I'm only going to retain the spacetimes that have a fixed number of connected components. So for example, if in the previous picture here, I decide that I'm only retaining the spacetimes that have 3 connected components, then the spacetime here would not be admissible. I would need here to add a little sphere or something like this in the middle. Okay, so I don't know. Yeah, so for example, if I only have things with 3 connected components and I try to compute a 3-boundary partition function, this would be admissible. This would be admissible. But something like this would not be admissible. This would be for a 3-boundary partition function. It turns out that if you do this in the Maroff and Maxfield model, you restore factorization. This was in 2020. Okay, then the other method is to say, well, I'm not going to change the rules of the game of the gravitational path integral. I'm going to allow every possible topology that I could think of to appear, but I'm going to add some extra contributions to the path integral. And the interpretation of these contributions would be things like branes and interactions between these branes. And the roles of these branes is to cancel the effect of the wormholes. So for example, the semi-classical path integral would give me a Z2, which would look something like this. And then it would have the wormhole. But then I could say, okay, I also add a third contribution, which would look like something like this. And this would be a bit like a brane interaction. And somehow this brane interaction is there to exactly cancel the effect of this wormhole, so that this wormhole leads to an obstruction to factorization, which is later canceled by an explicit stringy effect that I add to the path integral. Okay, so those are the 3 possible resolutions that I want to talk about today, which I think cover some significant part of the literature about this. And the idea is that since we went from a situation where there was no resolution to a situation where there are a lot of different resolutions, maybe there's a sense in which all of these resolutions are gauge equivalent. Maybe it's secretly the same to use each of these 3 methods, and there's some kind of structure that underlies their equivalence. So that's the plan for today. The plan for today is to come up with a systematic way of restoring factorization, because so far these ways that I've explained here are quite empirical. And along the way, what we will find is that there is an actual gauge group that interpolates between the three methods of restoring factorization that I just described. Okay, before I move on, is there any question?
I have a question about the Z cubed factorization. If you have this contribution with the wormhole, how does it factorize into a product of three terms?
Yeah, so you have to be a bit careful about the combinatorial factors when you do this computation. But basically, the idea is that, yeah, even for a one boundary partition function, you would also have to take into account only spacetimes with three topologies. So you would have closed spheres that appear in your path integral, even for a one boundary computation. And the symmetry factors between these closed spheres, if you're careful about them, will lead to factorization. It's not completely trivial. You have to figure it out in a bit more detail.
Sorry, can I ask a question? Can
Yeah.
you hear me?
Yeah.
I don't really understand why this factorization problem is really a problem, because the conjugate that you're using is not UV complete anyways, right? So I thought it was, say you're doing the Einstein-Hilbert path integral. It was just understood to be giving you some sort of coarse-grained answer to the, well, whether to some fine-grained observable. And then, of course, if I ensemble average or a coarse-grained, then I can have it such that each member of the ensemble might be factorized, but the average is not.
Sure, yeah.
So are you just trying to find an EFT that's a bit better and also has factorization? And then if so, does it still capture these coarse-grained observables, like, for example, the page curve that you would like to get?
Good. Indeed. So there's no factorization problem if you look at an ensemble of theories. The philosophy here is that nonetheless, if we try to do traditional holography, we don't want to be looking at an ensemble of theories. There are some low-dimensional models where there is some ensemble averaging. But in principle, if we want to make contact between those ensemble average models and the UV complete models, which are not ensemble average, we need to have a way to interpolate between the effective theory description, which sums over topologies and doesn't factorize, and the UV complete CFT, one member of the ensemble, which factorizes. And so the philosophy here is to try to come up with a heuristic to do that systematically. But indeed, if you stay at the level of the EFT, there is no problem.
But if they're all supposed to cancel, then when I do this interpolation, how do I know which ones to keep and which ones not to keep to get the coarse-grained average data that I would like to get in the low energy?
Yeah, so the idea is that you would only keep the semi-classical geometries. You start from something that just has semi-classical geometries, and you want to add something to it that goes beyond semi-classical physics. So if you want to only keep the coarse-grained part, you just don't add anything to it.
Well, for example, the first two rules, like 1 and 2a, seem like you can do it with saddle points, but you just disallow some of them. But then you said it's gauge equivalent to these more stringy brain interactions. So how does that mean?
Okay, maybe what I consider, I consider these two new rules as going beyond the semi-classical description. What I call the semi-classical description is something that sums democratically over all saddles, including wormholes. So even if you remove some saddles by hand or give different weights to saddles, depending on their topology, I consider that to go beyond semi-classical physics.
Okay, that makes sense. All right, thank you.
Okay, yeah, thanks for the questions. So maybe it's time to announce the basic idea of the talk. So the key idea, in order to do this, in order to systematically get rid of these wormhole issues, is that there is actually a very tight analogy that relates perturbative renormalization in quantum field theory to our problem of factorization. And so while we don't really understand factorization very well, renormalization is a much more familiar problem, and the idea is to leverage that analogy to say something systematic about factorization. So before going into the specifics, let me just tell you briefly how this analogy goes. So the first thing to notice is that in both cases, we have a sum over topologies. So in gravity, the sum over topologies, as we said, comes from the space-time amplitudes. So things of the form Zn, where we sum, we would have the contribution with, say, n disks, and then you would have a sum over space-times with wormholes of the space-time. So if I call a space-time with wormhole sigma, basically it's like inserting a sigma here. But the thing to notice is that in quantum field theory, there is also a sum over topologies. And the sum over topologies is given in the context of renormalization when you try to compute the effective couplings of the theory. So when you compute an effective coupling, what you do, let's say we're in phi3 theory, is that you have the tree-level diagram, which gives you the coupling before doing anything to it. And then you would also have a sum over 1 pi diagrams gamma that have the same boundary condition, but have some loops in here. So in both cases, both when we compute an effective coupling and when we compute a sum over topologies, we have, when we compute a spacetime amplitude, we have a sum over topologies. And both of these sums over topologies, moreover, have to satisfy a constraint. So in the case of gravity, we said that the constraint we want is factorization. We want to restore factorization. In the case of QFT, the constraint is the finiteness of this G effective. If we naively sum over diagrams, we'll get a divergent answer, and we don't want that. So finiteness. Now, the problem is that if we see both of these things as low energy effective theories, they will give rise to an obstruction to these two constraints. And both of these obstructions are topological in nature. So in the case of gravity, the constraint, as we said, was the wormholes. The wormholes are the topologies that pose a problem to factorization. Whereas in quantum field theory, the problems come from the loops. It's the loops in the diagrams that lead to divergences. So once again, it's a topological issue. Actually, I can even be a bit more precise. Like those constraints are topological in both cases, but they also share another structure, which is that they're nested. In renormalization, what makes renormalization difficult is that you can have divergences inside divergences. For example, if I look at this Feynman diagram in phi3 theory, the second loop here, the small loop, is contained inside the bigger loop. Similarly, wormholes can be nested inside wormholes. For example, if I have a pair of pants wormhole here, inside I can embed this little cylinder wormhole, which itself is an obstruction to factorization. Okay, so now we're looking at these two problems that look very similar, and we were wondering how to systematically fix factorization in the path integral. Wasn't exactly clear how to do that, but the good news is that in QFT, we've done a lot of work and we exactly know how to fix this problem of finiteness. In order to fix the finiteness of the couplings, we need to add counterterms to our Lagrangian.
Sorry, Elliott, I think I'm confused about your analogy about the nesting.
Yeah.
Because I feel like you're using a different definition of wormholes when you see that little cylinder inside a pair of pants. You're calling that wormhole, but I thought the relevant wormholes for us were surfaces that connected asymptotic boundaries. And that little cylinder you drew is not connecting asymptotic boundaries, right?
Sure. That's fine. I think you could say the same about the diagram. Here you could say that this big loop connects the asymptotic boundaries, but this small loop doesn't connect the asymptotic boundaries.
I see.
Yeah.
Okay.
But okay, I'm using, for this talk, a wormhole will not only be a wormhole between asymptotic topologies, it will be whatever is a non-trivial topology in the bulk. Okay, so that's the counter terms here. And the idea is that the way that we should try to fix the wormhole systematically in gravity is also by adding something that we called counter wormholes or stringy wormholes. In particular, in method 2b above, this third term here, we should really think of as being a counter term, as being an explicit counter term insertion that restores factorization. Okay, so now there's some fun math associated to this story, which is that the structure of renormalization is complex. It's complicated due to this nesting of obstructions. And it turns out that mathematicians worked hard to understand this structure. And what they found out is that there is something called a Hopf algebra that underlies the process of renormalization. And that Hopf algebra is called the Kohn-Kreimer Hopf algebra. And it turns out that for us, there will be an analog of this algebra, which is called the Fadi-Bruno Hopf algebra. And it will so happen that these Hopf algebras are the things that allow us to think of how to interpolate between the different descriptions. By descriptions, I mean the different ways of restoring factorization. Okay, so this is the analogy. Is there any question on the analogy before I move on?
Yes. Are these counter wormholes related to Hopf wormholes that were discussed in the context of SYK?
Yeah, exactly. You can see these half wormholes as being some examples of this counter wormhole physics that I'm going to introduce. Yeah. Okay, so how am I going to go about the rest of the talk? Well, the idea is that first I'm going to give everybody a refresher on renormalization, and more precisely on the proper way of doing renormalization, which is called BPHZ renormalization. So that goes for Bogolubov, Parasyuk, Hebb, and Zimmerman. So that's old physics from the last century, but that will turn out to be very useful. And then the idea will be to explain how to adapt their method to the gravitational path integral in a simple context. Okay, so let's go with a review of renormalization. So in renormalization, the basic objects that we want to look at is the effective coupling. So what do we do? Let's say we're in phi-3 theory for illustration. We want to compute an effective coupling. Well, we say that the effective coupling is the tree-level coupling here, plus a sum over gamma 1 pi diagram of, so here I'm going to introduce some notation. So I want some 1 pi diagrams that fits the asymptotic condition. And then what I say is that it's going to be the coupling to the power number of vertices of gamma times the unrenormalized value of gamma. So this is called the unrenormalized value. Let me just explain this equation briefly. So the idea is that this coupling here appears for each vertex, and we define this U to be the expression that you get when you just apply the naive Feynman rules to your Feynman diagram. You just don't put in the vertex insertions of the coupling. I encode them separately for notational convenience. There's also symmetry factors. I'm going to be cavalier about symmetry factors because it doesn't really matter for the main point. Okay, so this is the unrenormalized value of the diagram. And this notation U of gamma I will use again. So I just want to emphasize it. And so, of course, once we've computed this G effective, we find that it contains some divergences. But what renormalization tells us is that don't worry, it looks bad, but actually you can get rid of them systematically by adding counterterms to the Lagrangian, and you should see these counterterms as placeholders for our ignorance on what UV physics will actually come to the rescue. So it's very much a bottom-up philosophy, like the one that I'm trying to do with the path integral, where you start with a problem and you want a systematic way to, without a priori knowing the UV complete theory, fix that problem. Okay, so now here's the problem. The problem is that we said that in QFT in general, we have nested divergences. So, for example, if I look at, I guess, this diagram, I have this divergence, which is contained inside this divergence. And because of this, you could say, how do I add counterterms to the Lagrangian? Well, the first guess would be to say, for every diagram, isolate the divergent part, and then add a counterterm to the Lagrangian, which is exactly going to cancel this divergent part. That sounds natural, right? But the problem with this is that because you have to cancel things diagram by diagram, if you try to add a counterterm that cancels all of the divergences of this diagram, for example, you're going to double count the counterterms for this sub-diagram. And so you're not going to be canceling the divergences, right? Because there's going to be some double counting associated to this nested structure. So instead of doing that, we need a recursive method. We need to be more careful about how to cancel the divergences systematically, diagram by diagram. And this is what this BPHZ method does for us. Okay, so how do we do BPHZ? So the idea is that we start with gamma, a Feynman diagram. Oops, sorry. Apple Pencil's capricious today. So it's a recursive method. So we are going to assume that the counter terms associated to the sub-diagrams of gamma are already known. And it's only at the next step, well, at this step, we're only find the counter term associated to gamma as a whole. So we have gamma, a Feynman diagram, and we assume that the counter term associated to gamma for gamma inside gamma is known. So here I've introduced a notation. This is the counter term. The question of BPHD is how to compute the counter term associated to big gamma. Okay, that's what we have to do. So what BPHD tells us is that you can do two steps. The first step is to compute the so-called prepared value of the graph big gamma. So how do we do this? So this prepared value, which is denoted by R bar, is defined as being the unrenormalized value of that graph big gamma plus a sum over subdiagrams of the counter term associated to the subdiagram times the unrenormalized value of the diagram where I've quotiented the subdiagram to a point. I'll do an example soon, but I just want to give you the interpretation of this, which is that we start with the unrenormalized value, which has some divergences in it, but we throw into it the divergences that we've already canceled with the counter terms. So this second sum here is here to take into account the fact that there's some parts of this big divergence that we've already taken into account. This R bar of gamma is still divergent, but it's only residually divergent. The only piece of the divergence that is left is the one that doesn't come from subdiagrams, but is a genuinely new kind of subdivergence. And so then the step two is to say, we compute the counter term for which the renormalized value is finite. So the renormalized value R of gamma, renormalized value of the graph, is defined to be the sum of the counter term plus R bar of gamma. Let me just expand this formula because it will be useful later. This is U of gamma plus C of gamma plus a sum with gamma included in gamma of the C of small gamma, U of gamma over gamma. So here in this sum, we know this and we know this. We know this just because a non-renormalized value can be computed using the Feynman rules. We know this because the counter terms are assumed to be known because it's a recursive procedure. So the idea is that by asking that this side of the equation is finite, this gives us what the value of C of gamma should be. So find by imposing R of gamma finite. Okay, so maybe let's just do an example. So let's take this graph
But
in
Elliott,
5.3.
isn't there an ambiguity in fixing C that you can add a constant to C and still get the finite
Yeah, sorry.
R?
Let's say I'm doing MS bar or minimal subtraction. That's the choice of scheme. Yeah. Yeah, good question. So, okay. Let's do this example. So step one is to say that we compute the prepared value. So the prepared value of this graph is its unrenormalized value. So this part we just get by doing the regular Feynman integral. And then we add a correction by summing over subdiagrams. So here the subdiagrams are diagrams of this form, and there's two of them, right? One for this loop and one for this loop. So I get a factor of 2. The counter term of this subdiagram times the unrenormalized value of the diagram where I've quotiented the subdiagram to a point. So if I quotient one of the two loops to a point, I get a one loop diagram like this where I've quotiented this subdiagram to a point here. So you can really see these parts of the sum as counterterm insertions. Okay, now this is still divergent. So step 2 is to say, okay, now find the counterterm associated to this diagram by asking that the counterterm of this diagram plus R bar of this diagram, which we computed at the step before, is finite. And we're doing a minimal subtraction. Okay. Is there any question before I move on? All right. Okay, so what does this BPHD procedure output for us? Well, it starts with the unrenormalized values. Those are inputs because they just come from the Feynman rules. But after iterating this for all diagrams, for each diagram, I will be landed on something that gives me both a counterterm value for this diagram and a renormalized value for this diagram, which is R of the diagram. And now the question is, how can I use these counterterm values and these renormalized values to produce finite effective couplings? So given U, which was the unrenormalized value, C, which was the counterterm, and R, which was the renormalized value, how do I produce finite effective couplings? Well, there's different methods, once again, and I guess you see where I'm going. So the first method is to say, well, one thing we can do is just directly resum all the renormalized values of the diagram. So what I mean by this is to say that the renormalized effective coupling is the original effective coupling G plus a sum over over gamma 1 pi, sorry. So here I put a gamma 1 pi of G to the power number of vertices of gamma, and then renormalized value of gamma, which is the finite value associated to gamma that BPHZ outputs. If I do this, this sum is manifestly finite because all these terms are finite, and so I'm done. I don't need to do anything else. Now, that's not usually what we do when we actually try to renormalize a quantum field theory by hand. And the reason is because these R of gammas are really difficult to compute. Those are things that you need to do things iteratively for all subgraphs before gamma, before getting this R of gamma. So we don't usually write things like this. Instead, what we usually do is that we do things in 2 steps. In the first step, we resum the counterterms into bare couplings. And then in the second step, we resum the unrenormalized values, but instead of inserting the first coupling, the naive coupling that you have in the Lagrangian, you insert a bare coupling instead. So let me put this in equations. So first you compute G bare, which is equal to G plus a sum over gamma 1 pi of G to the power number of vertices of gamma times the counterterm of gamma. So I resum all of my counterterms into a bare coupling systematically. Now this quantity is divergent because the counterterms contain some divergences. And then the second step is to say, well, now I can compute my G effective renormalized by saying that it's G plus, sorry, G bare plus a sum for gamma 1 pi of G bare to the power number of vertices of gamma times the unrenormalized value of gamma. So this unrenormalized value you just get by the Feynman rules. It's divergent. This G bare is also divergent, but the miracle of renormalization is that all these divergences are going to cancel out, and in the end, you're going to get the same answer as here, which is a manifestly finite answer. Then there is a third method, which is you don't have to, throw in the counterterms in the bare coupling and then expand in terms of the bare coupling. You could just do something much more naive, which is you could painfully enlarge your set of Feynman diagrams so that you also allow new kinds of vertices that insert arbitrary kinds of counterterms. So it's summing over more diagrams that have more counterterm insertions. And if you do this, it's like expanding this sum explicitly. And so, of course, you will get that all the counter terms cancel the divergences and everything will be fine. Okay, so those are the three things you can do once you're handed the values of the counter terms and the values of the renormalized values of the diagrams. Of course, the point is that these three things should be secretly the same as the three things that I said in the beginning. So what makes these three methods equivalent? I think this is a good place to introduce the mathematics behind these three methods. So the idea is that we can see these unrenormalized values, these counter terms and these renormalized values as functions that go from the Feynman diagrams to the complex numbers. So, U takes as an input a Feynman diagram and outputs a number. Moreover, it's multiplicative on disconnected components. So that motivates to define a law on functions on Feynman diagrams. So I'm going to take two functions, f1 and f2 of Feynman diagrams, and I'm going to say that their star product, f1 star f2, is going to be given by f1 of gamma plus f2 of gamma. Sorry, this is a function on diagram, so it takes the diagram as an input, plus a sum over subdiagrams of f1 of the subdiagram, f2 of the big diagram divided by the subdiagram. Okay, so this is exactly the formula that I was writing to rewrite the renormalized value in terms of the counter term and the unrenormalized value. So with this notation, the renormalized value of the diagram is the star product of the counter term of the diagram and the unrenormalized value of the diagram. Well, sorry, of the counter is the star product function applied to the diagram. That's more correct to say. So of course, the motivation for this formula is the BPHD procedure itself, but the idea is that mathematically, group laws that, well, multiplication laws that look like this secretly come from something called a coproduct on the space of Feynman diagrams. So this is associated to a Hopf algebra structure on the space of Feynman diagrams, which I'm not going to describe in detail. But the basic idea is that you can compute the coproduct of a Feynman diagram by the following formula. So you see that if I apply the function f1 to the left of this tensor product and the function f2 to the right of the tensor product, I will get exactly the formula that I wrote above. So in a very clear sense, this group law is dual to the coproduct law. So you can show that this law is associative and admits inverses, and for this it equips the set of functionals on Feynman diagrams with a group law. Now the idea is that we can understand the equivalence between the three methods that I said before as coming from an action of this group of functionals on diagrams onto the space of couplings. So the way that I define the action of a function f on a coupling G is that I say that the function f acting on G is equal to G, which corresponds to this diagram, plus a sum over gamma 1 pi of G to the power number of vertices of gamma times f of gamma. So, for example, method 1 was telling us that G effective renormalized was equal to the renormalized value acting on G. To compute G effective renormalized, what I could do is just take the renormalized value of each diagram and sum them. And then the sum was manifestly finite. On the other hand, method 2a was telling me that I could also write G effective renormalized in two steps, which is that I would resum the unrenormalized values, but acting on the bare coupling instead. And the bare coupling itself, I could write has the counter term acting on the first coupling. So what I do when I compute G effective renormalized with this method is that I resum the counter terms into the couplings. That's this first arrow. And then I resum the unrenormalized values, but with insertions that correspond to the bare coupling. There's this second arrow here.
Sorry, Elliott, can I just clarify one thing? When you write this
Yeah.
little arrow for the group action,
Yeah.
is that just supposed to be a special case of the multiplication rule? So you think of G itself as a function on graphs, is that right?
Of the what rule? Sorry.
Yeah. When you write F arrow G, can you explain that arrow again? Like, are you just multiplying capital F and little g, or what's the arrow mean here?
Good. Okay. So F is a function on diagrams, and G is a particular value for your coupling. So the idea of F acting on G is that you use this function of diagram to change the value of your coupling. So it's an action of the function F on the space of couplings.
I see. And you just define, I misunderstood. So you wrote the double dot there. I mean, you're defining this action by that formula.
I define it by this formula. Yes.
Okay, it didn't come from anything previous to that. Okay, I
Yes.
see.
So the idea is just that I want to define it because that's what changes my coupling when I act with renormalization transformations.
I see.
And so, the first way is saying, well, and basically in spirit, what this arrow does is that it just resums all the 1pi diagrams. So what I'm saying is that, I could either resum all the 1pi diagrams with their renormalized value coming from EPHZ, or I could do it in 2 steps. I could first resum all the 1pi diagrams with their counter terms, and that will give me the bare coupling. And then using the bare coupling, I resum all the 1pi diagrams with the regular Feynman rules. And then that gives me the effective renormalized. Of course, the miracle of renormalization is that those 2 things give me the same results. But recall that by the formula that I gave above, R was equal to the product of C and U. So really what this is saying is that C star U acting on G is the same as acting first with C and then with U on G. This is the definition of a right group action. So the fact that those methods are equivalent is just the fact that this formula defines an action of the group of functionals on the couplings. In particular, seeing this action, what I can also do is now very easily interpolate between the different prescriptions. So for example, what I can do is I can say, well, what if I multiply here by C inverse, and I multiply here by C? Then I will basically land back on this formula. So by inserting transformations either here or here, what I will find is that, sorry, I should have said multiply here by C. So by inserting group transformations in this formula, I can interpolate between the different ways of writing down the action. So that means that I can really see this group of functionals as a gauge group that interpolates between the different ways of renormalizing my coupling. Okay, so that was the most technical part of the talk, I think. Now let me just get into what it means for the gravitational case. And essentially, now that you understand the structure, it's very easy to do the same thing for gravity. It's actually easier. So let me just give you a simple model where we can do this. So the model that I will take is the Maroff-Maxfield model without closed spacetimes. So the rule is the following. We want to say that for n asymptotic boundaries, the topologies that will appear in our gravitational pathing rule are only genus 0 topological surfaces without closed components. So let me give you an example. If I want to compute something with 3 asymptotic boundaries, I will get this topology, I will get 3 copies of a topology that has a wormhole like this, and I will get this topology. Okay, those are the topologies that would contribute in this model. I don't count topologies that have closed spacetimes, and I don't count topologies that have higher genus or anything like that. It's just a toy model. There's no obstruction to doing the same type of thing that I just mentioned to more complicated models, but for the purpose of the exposition, I think it's clearer to just look at this simpler model. So now, okay, this tells me the kinematics. This tells me what I'm summing over. It does not tell me the rules of the game. It doesn't tell me the dynamics. So what are the dynamics? Well, the idea is that a spacetime with n connected components is going to contribute lambda to the n to the path integral, where lambda is some fixed number. Okay, so for example, here this has 3 connected components, so it contributes lambda 3. Then there's 3 of them, and they have 2 connected components, so they contribute lambda squared, and this contributes just lambda. Of course, lambda cubed plus 3 lambda squared plus lambda is not lambda cubed, so there's a factorization problem in this path integral. And now we can ask, how do we systematically fix the factorization problem of the path integral by doing something analogous to what I said before. So the idea is that we're going to make an analogy where we're going to think of this lambda to the n as the coupling Gn, which is a coupling that is associated to n incoming propagators. So in quantum field theory, when you have n incoming propagators, you have a coupling associated to that, to this vertex, which is Gn. Well, here we're sort of going to think of the middle of the spacetime as a vertex. And we're going to think of, for example, here, like 3 incoming spacetimes as the 3 propagators that get into this vertex. I'm going to be very simple, so I'm going to have completely trivial Feynman rules apart from the vertex. The only things that are going to matter are the vertices. So in particular, the unrenormalized value of all topologies, sigma, is going to be taken to be equal to 1. This is just saying that the only contribution of the topology that appears here, for example, will be the vertex contribution, so its number of connected components, and then multiplied by 1. This is a bit different from the case of a diagram where the vertices contribute a number, but then we also have the rules for the propagators. Okay, and then of course, the thing is that the analog of the effective coupling is going to be Zn. So the basic idea is that I can also define a BPHZ procedure for this theory. And I guess now that you know that really what underlies this BPHZ procedure is this group structure on functionals on diagrams, or alternatively coproducts on diagrams. Well, the idea is that I can define a similar coproduct on the space of wormholes. So let's do an example for a pair of pens. Let's take this pair of pens. The idea is that I can define its coproduct as being equal to these 3 disconnected components tensored with a pair of pens, plus the pair of pens tensored with these 3 connected components, plus 3. Sorry, my Apple Pencil is not working today for some reason.
Elliott, there was a little flashing message saying there were only 4% battery left on your pen.
Oh, okay, yeah. I'll try to plug it as often as I can then.
Sorry.
So yeah, sorry, plus 3 times, okay, and so I'll draw the picture and then I'll explain what it means. So, oh, sorry, I should have written 3 disks here. Yeah, plus 3 times this tensor with this. Okay, so what do I mean by this? I mean that the idea.
Before you go on, I have a very simple point of clarification. I'm just confused by the sentence above them when you say lambda n is the same as Gn with n incoming propagators. I'm a little confused because it sounds like you're saying the the coupling that has n legs is lambda to the power n, but above, oh, I'm sorry, I think I understand. So I'm confused. And above you showed that when there are n components, the actual value is not lambda to the power n, right? So
yeah, exactly. So
this is
well,
the tree. This is the one without
sorry.
any. Yeah.
By above, do you mean here or somewhere else?
So I'm just confused about that and the sentence below it. Yeah.
Oh, okay. No, so this has 3 components, contributes lambda to the 3.
Yeah.
This has 2 components, contributes lambda to the 2. This has 1 component, contributes lambda. Does that solve the confusion? I don't think so, right?
No, that's fine. It's just that below it, it seems like you're calling lambda to the n. You're calling that Gn, which is Gn meant to be the total number of diagrams with n incoming components? Maybe if you define Gn for me, then I'll
Yeah,
understand better.
Gn means that it is the number that you insert in your Feynman rule when in your diagram you have a vertex with n incoming propagators. So here this would be G4.
Right. And what does it look like in terms of wormholes? It's only the first diagram on the above that you would call Gn, G3?
So I'm saying that here the analog is you want to think of this gravitational path integral as a theory with infinitely many couplings. And the couplings are labeled by the number of spacetimes that appear. Sorry, of connected components that appear in your spacetime. So just like the couplings are labeled by the number of propagators that intersect in quantum field theory, here your couplings will be labeled by the number of connected components that appear.
Okay, that makes sense. Okay, right. You're not counting the number of asymptotic boundaries. You're counting the number of connected. Okay, sure.
Right, I'm being blind to the asymptotic boundaries, and then I'm saying, okay, well, just like in the Feynman diagrams, you could also have a contribution coming from the propagators, and that would be like having contribution coming from what happens at the asymptotics. Here, I'm saying I'm even going to consider a simpler theory. I'm going to assume that the only contribution comes from the vertices. So
Okay.
from the perspective of the theory, whether this is a wormhole or a 3-legged thing, or this doesn't matter. It's going to contribute the same. The only thing that matters is the number of connected components of spacetime.
Okay, I'm happy. Thank you. Thank you.
The reason why I'm doing this is because this is what is found in this Maroff-Maxfield theory, where you get the Euler characteristic in your action and so on. Okay. Yeah, thanks for the question. So the idea is that under this analogy, you want to define a similar coproduct on wormholes, and maybe for a general wormholes. Okay, yeah, definitely my battery is low for this pencil. I'm sorry. So for a general wormhole, the way that you're going to define the coproduct is that you're going to say that the coproduct of a wormhole sigma is going to be equal to sigma tensor 1. Sorry, for all intents and purposes, this is 1. This is a mathematical subtlety where I'm not writing it as 1, but it's not very important. So you can think of this and this as 1. Plus 1 tensor sigma plus the sum over all embedded wormholes little sigma of little sigma tensor with sigma where I've removed little sigma. So let's see what this gives here. Here I have this pair of pens. So those are the 2 trivial terms. And then we said in the beginning that in this pair of pens, I can embed some sub-wormholes which look like cylinders. I have 3 possible sub-wormholes like this. So this is the combinatorial factor of 3. This is the sub-wormhole that I embed. And now I'm saying that if I pinch off this part of the spacetime, I'm going to be left with this piece and this piece where the sub-wormhole has been pinched off. So this is what this gives me. Another perhaps more telling graphical way of writing this equation is saying that I can rewrite, maybe let me erase, well, okay, I'll just write it down. So I can rewrite this equation as, the wormhole where I haven't pinched anything, plus the wormhole where I've pinched everything, but now I have a counter term associated to this pinching. So that is the second term here, plus 3 times the wormhole with the disk, where once again I have a counter term associated to the fact that I've pinched this sub-wormhole. So this is very much like the stringy contributions that I was mentioning in the beginning. So what do we do? Well, if we start with a wormhole, we first compute its prepared value. So let's say that the prepared value of the pair of pans is going to be the unrenormalized value of the pair of pans, which we said was just 1, plus 2 times the embedded 3 times the counter term associated to the embedded wormhole times the unrenormalized value of the pair of pans where I've removed the embedded wormhole. So that gives me the prepared value. Now the analog to renormalization is saying that this prepared value is not 0. So this is a wormhole topology. It's an obstruction to factorization, so we would want it to be 0. But if we compute this, we can find, recursively by using the counter term that we found at the previous step and so on, that this is non-zero. So the second step is that we want to compute the counter term associated to this pair of pans. So, something that we would think of as being the same as this three-legged counter term here, such that the renormalized value of the pair of, the prepared value of the pair of pans plus the counter term of the pair of pans, which is equal to the renormalized value of the pair of pans, equals 0. So note that there's a slight difference to renormalization here. In renormalization, the situation was a bit more complicated because there was a part of the contribution of each diagram that was not problematic. There was a finite part that was not divergent and just okay to be there. Here, there's no such thing as being divergent in the cutoff or not. It's really we want to reinstore factorization. So we want the renormalized values of the wormholes to not just be finite, but be 0 on the nose. Okay, so what we want to impose is that those counter terms exactly cancel this prepared value for each step and not just the divergent pieces. But up to that, it's the same, and you can recursively compute the renormalized values and the counter terms of all the wormholes. And now we can say, well, what is the analogy of the 3 methods that we said before? So we said that method 1 in the QFT context was saying that the renormalized effective coupling was the coupling plus a sum over subdiagrams of, over gamma 1 pi of the coupling to the power number of vertices of gamma times the renormalized value of the diagram gamma. So here, the same thing that we can say is that the wormhole amplitude with n boundaries is equal to the contribution of n disks, which is the thing that doesn't contain the topological obstructions, plus a sum over sigma spacetime with wormholes, so which contains obstructions, of lambda to the power number of connected components of sigma times r of sigma. But now we said that the renormalized values of all spacetimes with wormhole were 0 by construction. So with this method, we're resumming a lot of zeros, and that's basically saying that we're excluding the wormholes by hand. So the analog of directly resumming all the renormalized values diagram by diagram is the fact that we're saying that we are killing all the wormholes by hand. On the other hand, method 2a, we said was a bit more subtle. It was going first from G to G bare, and then from G bare to G effective renormalized. So in this first step, what we did was that we changed the value of the coupling. right? We went from something finite to something that contained counterterms. Here, recall that the analog of our original coupling is lambda to the n. So what we're saying is that we're changing this value of lambda to the n. In other words, the contribution of n connected components is no longer lambda to the n. What is this saying? The nice thing about lambda to the n was that if I have n connected components, I can think of it as, one lambda for each of the connected components. It has a strong flavor of locality. It respects the locality of the path integral in the fact that the contribution of a spacetime will be multiplicative on its connected components. If I start messing with this structure, that means that the path integral becomes non-local. And in particular, there is a non-trivial weight that doesn't come from any individual component, but instead comes from the number of connected components as a whole. This is the same as this method that Maroff and Maxfield were saying in the beginning, where they said that the contribution of a spacetime with n connected components was 0 unless it was a particular number of connected components. So this is the same type of non-local rule as the one that was introduced by Maroff and Maxfield. And it turns out that in our model, if you compute what you get for this lambda to the n, you actually get exactly the Maroff-Maxfield prescription up to a subtlety which is due to the fact that they're including closed universes and we're not, but it's basically the same thing. So, this gives rise to this Maroff-Maxfield prescription about the number of connected components of spacetime. And then, of course, we had this method too.
Elliott, you're saying it doesn't restore factorization, right?
It does. It does.
Okay.
So in the beginning, if what Maroff and Maxfield were saying was that you could still sum over spacetime with wormholes, but only allow spacetimes with a specific number of connected components. And if you do that, then you find that you restore factorization. So here, if you do this from our BPHD algorithm perspective, you'll land on exactly the same prescription, and in the same way, it will restore factorization. Then there is this method 2b, which is to say sum over more diagrams. And so in our context, it is resumming, it is about extending the space of geometries that we sum over to explicitly include these counterterms. So for example, instead of just summing over this plus 3 times this plus this, we would also have, then you would have various choices for example, you would have a term that looks like this. Then you would also have some terms that look like this and so on. Okay, and those terms here are explicit counterterm insertions, but those counterterm insertions were matched with brain interactions in the literature. So we can really think of these counterterm insertions as brains, at least in some simple cases. Okay, so that's the punchline, is that you can basically recover all these ways of restoring factorization for a gravitational path integral by adapting the methods of renormalization to the case of gravity. And the underlying structure is a similar, coproducts and group law on functionals on topologies. So in the same way, you can think of the equivalence of these different ways as coming from an action of that group and so on. So let me just finish with some outlook. So first, the obvious thing to do is we did this for Maroff-Maxfield, but we would like to do this for more complicated models. So I know that, for example, Maroff-Maxfield is topological, but what if we add some metric structure? I know that in this audience, there's probably a strong interest in 3D gravity. So can we do the same for 3D gravity? There, the sum over manifolds is a lot more complicated, but recent work has shown that you can organize it in terms of a sum over diagrams as well. So maybe there's something to be done there. So that's related to this higher dimension story. We can also try to go the other way around. So today I talked about the factorization of the partition function, but one could also talk about the factorization of the Hilbert space, which suffers a similar problem. But then that requires cutting your surfaces. And so going to higher codimension. So is there some form of categorification of the structure that also takes into account the factorization of the Hilbert space? This is, of course, all related to the fact that there are a lot of null states in quantum gravity, in the non-perturbative regime, that we don't see in the gravitational path integral. For example, you can interpret the fact that there is factorization as the fact that there's so many null states in the Hilbert space of a closed universe that it's one-dimensional. So can we interpret the structure of these null states in terms of this structure that we found? Now that they're, especially in the current context where these null states are very important for a lot of things. This last comment that I wanted to make is more for the more mathematically minded people, which is that this Kohn-Kreimer group or Hopf algebra that I described in the case of renormalization is very related to some deep problems in mathematics in number theory, because you can see that there's a sort of branching structure to that group, which is that because I have nested divergences, you know, I can nest things in different ways, and it's like going down a tree. This branching structure can also be found when you study the extensions of the field of rationals. And you can, you know, do more and more complicated extensions by nesting them in different ways. And this is at the source of a strong similarity between the structure that I described today and a structure in number theory called the absolute Galois group, which is the Galois group of all possible extensions of the rationals. So this has been very well studied in mathematics in the context of renormalization, and it would be interesting to see if we can learn something from these mathematical developments in the case of quantum gravity, now that we're not summing over diagrams, but we're summing over different kinds of topologies, which are manifold topologies. Okay, I just want to end up with a sort of general philosophy that this talk was very much embracing and that I think is interesting, which is that it looks like we could go pretty far here in terms of restoring factorization, which is a completely UV constraint, by just looking at the semi-classical theory and studying its symmetries carefully. So here the symmetries was this nesting of the topologies inside each other. And just by using these symmetries, we were able to, you know, leverage that to apply this BPHD procedure and restore factorization. So here's a context where there's a completely UV property that can be restored from the bottom up, from first principles, by studying the symmetries of the low energy theory. And I think an interesting question is how far can we go by doing things like this? Can we start by something that looks like semi-classical physics and derive features of string theory, like these brane interactions, by just asking for consistency with the holographic principle? This was an example of it, and I think it's an idea that's worth exploring further. Okay, thank you. This is it.
Okay, thank you very much, Elliott. It was a very nice talk. Are there more questions from our audience out there in Zoom land?
I have a question.
Go ahead.
Hi, Elliott.
Hi, Lisa.
So in the 2B, the final result that you got for the 2B case. So that corresponds to when this example in JT gravity where you unglue like the double trumpet, right? So you put some special type of brain with a fine-tuned coupling.
Yes, exactly.
So do you actually get like the value of that coupling or of that weight for these brains with using renormalization?
Right. So here I'm not in JT, so I don't think I would get exactly the same thing. But nonetheless, yeah, I get an explicit value for that coupling. Yeah.
Okay, and all of this in this, well, I don't know exactly what's the difference between this model and JT gravity besides the genus.
Right, so this model is completely topological. So the only thing you need to compute the action is just the topology of the bulk. Of course, this is not true in JT because you need some metric information, like you have information about the dilaton and so on. It's not just a topological theory. So
okay.
So you have like an extra passing rule to do over each saddle, whereas here I'm just giving one value to the saddle. So my model is much more stupid than JT. But,
okay, but in principle, you should be able to derive, if you
yeah,
apply this to JT.
Okay. Yeah, I don't think there's any obstruction because you can do the path integral like on each saddle separately, and that will give you a number, and then you can plug that number into that topological method, and the same thing should follow. So yeah, I think it's fine.
Okay, thanks.
Thank you.
Any other questions? So now actually, Elliott, could you go up a little bit? Because I think there was something that I didn't quite catch. I think you were trying to define a code product, right, for these geometries.
That's right,
yeah.
yes.
So it's like, because earlier you were saying there was some kind of star product that was the dual to some co-product.
Mm-hmm.
And I wasn't if sure if I understood. Did you also use that below when you talked about the realization, this star product stuff?
Yeah, yeah. So the star product is really the same as the co-product. So the way that you go from the co-product to the star product is to say that you have two functions, right? The star product. Okay, let me erase something so I can write it down for you. So the star product. Sorry. Yes, the star product would tell you that if you take two functions, f1 and f2, so those are functions on the wormholes. Their star products applied to a given wormhole topology is given by f1 of the wormhole plus f2 of the wormhole plus a sum over sigma sub-wormholes of f1 of sigma times f2 of sigma minus the sub-wormhole. On the other hand, here you have the coproducts formula, which takes a topology, so directly a wormhole topology, and gives all the possible splits. So you're going to have a left factor and a right factor. If I apply f1 to the left factor of this and f2 to the right factor of this, I will get back this formula.
I see. But and the point is again that this star is gonna help you interpolate between the different types of renormalization. Is that because in the previous
Yeah,
right, that's what you said, right? That you can kind of move between the different methods of renormalization by just multiplying and doing inverses and so forth.
yeah. So the way that you can see it is, okay, so we had this fundamental formula that the renormalized value of a diagram or a wormhole, so in the case of the wormhole, it's just 0, is equal to the counter term starred with the unrenormalized value applied to the wormhole. Right, this is just saying BPHD. This is saying that renormalized value equals counter term plus unrenormalized plus this sum over subdiagrams.
Yeah, okay.
And then the idea was that we had this action, right, which was resumming things into the coupling using one of these functions. And we were saying that, you know, the fact that the fact that I can first resum the counter term into G and then resum the unrenormalized value into G, this is the same as saying that I can just resum the renormalized value into G. But this is equal to C star U applied to G.
Right. Okay, yeah. So I just make sure that it works the same way.
Yeah, oh yeah. No, sorry, yeah. Everything works exactly the same way. It's just that now the G's are the contributions of n connected components.
See. Right. So can I just understand maybe just because I think can you go down also a little bit in your the three steps now of different wormhole renormalizations, right?
These three things, yes.
So are you um so is this supposed to produce the actual value of the counter terms? This like this method here? You're supposed to tell me what the value of the counter terms are. Is that
Oh,
part of what
sorry.
it
So there's
is?
two steps, right? The first step is you run this BPHZ here. So that tells you the values of the counter terms recursively.
I
So
see.
that doesn't require anything on the couplings or methods or anything. It just hands you with data, which are the counter terms and the renormalized values.
But you have to compute them, right? Or you have to figure
Yeah,
them
so you
out.
compute them with these methods.
I see.
You do the prepared value. It gives you the count. So that's something you can compute from the previous steps. And then you compute the counter term by asking that the prepared value plus the counter term has to be 0.
It's the same thing. Okay, I see. It's just okay. I understand.
Once
Yeah.
you have that, then you're equipped with your data. You have all the counter terms, all the renormalized values. Well, here the renormalized values are a bit boring because they're all 0. And then you can throw them into the coupling in different ways. And those are
Right,
the
right.
two methods.
I see. But can I maybe ask one more considered question? Is I'm not sure I will call this, you wouldn't say this UV completion of the theory, right? I mean, in the same way the counter terms are not
Well,
UV
okay.
complete. RG flow goes one way, right? It goes down in energy, not it doesn't go up,
Well,
right?
I guess you could say that, in some cases, like in asymptotically free theories, you start from something that is not UV complete, but it turns out that when you add counterterm, the theory becomes completely well-defined,
Oh,
right?
okay.
So I think this is kind of the hope that we could do something similar where we start from something that clearly has problems with holography, cannot be the UV complete answer, but just by studying these problems and their symmetries, we could work our way up to get something that's UV complete. So if you define factorizing as UV complete, then I guess this is UV complete. But of course, it's a really stupid model, so I don't think we can
But
claim it too.
to be very specific, suppose there's something we know, like, n equals 4 super Young-Mills. Maybe there's some CFT, maybe there's some D1, D5 CFT where we know it's holographic, right?
Yeah.
And instead of giving you the actual boundary quantum theory, I just give you the rules of the gravitational path integral, and you try to run this algorithm for me. Do you think you can land back on n equals 4 super Young-Mills from?
I mean, I don't know. The thing is, you will have to do a lot more things, right? Because it's n equals 4 mills has more properties than just factorizing. So
Right.
that, but nonetheless, there's a lot of properties of locality. There's things like crossing, right? Like how do you correct the gravitational path integral into something that satisfies crossing? This feels like a similar type of question, but that requires doing more slicings of your path integrals and so on.
I see. No, that's precisely my point. I feel like there's some constraint that's missing here because when you have these counter terms, you mentioned call them branes, but surely we have a definition of branes that's sort of independent. Like, for example, could the non-locality you impose be too much, right? Like, if you're allowed to impose arbitrary non-local behavior, then
Yeah.
you could probably solve almost any constraints. But what's difficult, as you mentioned about crossing, is that once you impose locality, that's much stronger.
Yeah.
Then
Another way I would say this is that factorization is the coarsest possible locality requirement that you can impose.
yeah,
But
right.
in truth, it's not just like local in terms of the fact that it factorizes on disconnected systems. It's actually local as a field theory, and that's much stronger. But nonetheless, there are some constraints like crossing that I'm not very familiar with the literature, but I know people have thought about crossing and the path integral. Uh, and it would be interesting to see if, yeah, in the same way we could find a way to correct the path integral to respect
Wait,
some
sorry.
local.
Do you mean crossing imposed on the bulk theory? Because that's what I think that's what Dan and I and Lisa were doing. That we're showing that the sum of a topology, the sum of three topologies,
Mm-hmm.
were of different types. There was a type that was associated to summing of topologies where two manifolds times a circle. Those are more like the sum of topology for JT. But then there was another type of summing
Okay.
over topologies. It's not just this tensor product, a direct product of manifolds. And those manifolds they were quite literally imposing the crossing of the crossing symmetry of the boundary CFT.
Right. Yeah. Yeah. So that's what I had in mind, that you have this extra sum. And I wonder if we can think of these extra manifolds that appear as some kind of thing that we can derive from the bottom up in order to impose crossing. I'm not too sure. I don't know if that's the right way to think about them.
I see. Okay, I'm sorry that I know I've monopolized the conversation. If let me just maybe end the official recording part here, and then if people want to stick around, if you have time, we can chat more.